Hello, everyone. Welcome to the machine learning course provided by the Cybernetics Department of NRNU MFE. Today, we will look at some of the basic concepts of supervised machine learning that are underfitting, overfitting, and generalization. In the first part of the lecture, we will consider a little bit of theory, and in the second part, we will look at a simple example that demonstrates how underfitting and overfitting occurs. So let's start. So first, we consider the supervised learning problem statement, and then introduce the concepts of inductive bias, training, validation, and test samples, and underfitting, overfitting, and generalization, and finally illustrate these concepts with a simple linear regression model. There are two main branches in machine learning: supervised learning and unsupervised learning. There are also many other types of machine learning paradigms, but these ones are the most common. In supervised machine learning, we have some objects given from an instance domain, for example, fruits, and for each object, we know a target value given from a response domain. It's supposed that we don't know how these target values were assigned to the objects, but there were an oracle that knew how to do it. So we can give an object to the oracle, and he or it will give us a corresponding target for this object. If we use the oracle to obtain the targets for n objects, we will collect a sample D of n pairs. Each pair is an object and corresponding target. The aim of supervised machine learning is to model this mapping that the oracle knows and performs. This is a mapping F from instance domain X to the response domain Y. And we know about this mapping only n points. Mathematically, it's a classical function approximation problem. So the supervised machine learning task is the function approximation task. If the set of responses is continuous, that's for each object we have continuous target, then the problem is called as regression task. And if the set of responses is discrete, then the problem is called as classification task. For example, if X is an image of fruit and Y is its quality measure or freshness or price, then it's a regression task. And if the responses are class labels, for example, apple or orange, then it's classification task. As a result of supervised machine learning, we obtain some approximation of function f. That is an approximation of Oracle's knowledges about how to assign targets to their input objects. This approximation is called as hypothesis. And there are two main questions. First, if we construct some hypothesis H, how can we know whether it's good or bad hypothesis? We need some quality measure. And the second question is how to construct hypothesis. If you are familiar with the approximation theory, you can note that the machine learning task is ill-posed task. It means that there are many solutions, indeed, infinite number of solutions. That is, there are infinite number of functions that satisfy the points from sample D. And the reasonable question occurs here: which function from this infinite set of functions do we need? Which one is the best, or at least good one, and how we can find it? Well, to make the ill-posed problem to be mathematically correct, we need some assumptions about the solution. So we will find the function that approximates the sample D and at the same time satisfies these assumptions. In such way, we can reduce the set of possible solutions or even make the solution to be unique. It's easy to guess that the quality of the solution found will depend on the assumptions used. These assumptions are called as inductive bias. We need to define inductive bias to solve the supervised machine learning problem. And it's crucial for the quality of the machine learning model that will be obtained. In practice, we define inductive bias when we choose the class of hypotheses. It's a class of functions that will approximate the given points from the sample D. And the machine learning algorithm performs the search of the optimal function from this class. But what does the optimal solution mean? Usually in the approximation tasks, the more accurately the function satisfies the given set of points, the better it is. But is it really what we need? Why do we need to construct a function that passes through the given set of points as accurately as possible? We already know the targets for this set of points. The oracle has given them to us, and there is no need to predict targets for these points. The true goal is to construct the model that could predict the targets for new, unseen points. But in machine learning problem, we try to find the model that predicts well only the points with known targets, so-called training points. And here the reasonable question arises. Why the model fitted on the training data will predict well the target for unseen data? There is no simple answer to this question. The short answer is there is no guarantee that the model fitted on the training data will predict unseen, so-called test data with high accuracy. We can only hope that our inductive bias was good and the trained model will work well on unseen data. And here we need to introduce the concept of generalization. By definition, it's the ability to accurately predict responses for previously unseen data. If the model doesn't predict responses well on either training or test samples, it's a case of underfitting. One of the reasons of underfitting is bad inductive bias choosing. So a good model just doesn't exist in the given class of models. If the model predicts responses well on training data and works badly on test data, it's the case of overfitting. Both models are practically useless because they cannot perform well on unseen data. And the perfect case is when the model works well on both training and test samples. It's called that the model has good generalization capabilities. The estimation of generalization capabilities is one of the important tasks in machine learning. The validation sample is usually required to do it. The validation sample is considered as a part of training sample, and cross-validation techniques are used here. We won't consider these techniques now. They're out of the scope of this lecture. Now, we illustrate in practice what is underfitting and overfitting, and how to control them. So we use Python in Google Colab. It can be any other environment. So first, we import some commonly used models. It's NumPy for working with vectors and matrices and matplotlib for visualization. Also, we import linear regression model from scikit-learn and function to split data on training test samples. The target function that we deal is here. It's a polynomial function. So here we define this function and prepare data set. We generate random numbers from a given range, reshape the sample to be column vector, and calculate the function values for the points generated. Then we split okay, here, okay. We split it into training test samples and visualize. So we use matplotlib function. Here we will obtain a plot of this function. The train points are blue and the test points are red. We see that it's really looks like a polynomial, and we expect that our machine learning model will reconstruct this function based on the training points. What can we note here? So here and here, there are no training points. And the model doesn't know what should be there. Theoretically, there can be some oscillations or some complex dependency or something else. We know that the true function is a polynomial, and here must be a smooth line. But the model doesn't know about it, and really we also wouldn't have known about it if we hadn't generated the data. But we can impose the inductive bias and assume that the function under modeling is quite simple, and we can define the class of hypotheses as a set of simple polynomials of some small degree. First, we will search the solution in the class of simple regression models. It's degree on that. It's a polynomial of the first degree. We create a linear regression object and fit the model using the training data. The unique regressor X is the data that we have generated. And then we make predictions using the trained model with the function predict. Well, here we run this game, and we can see that this model, it's a linear function, it underfits the data. The linear model is too simple to model this data set. The inductive bias that we have posed with the class of linear models is too strong. It's not sufficient to model this data. And now let's weaken inductive bias and define the class of models to be polynomial of degree k. So we use k regressors in the regression model that are powers of x up to k. So the input to the method fit is the matrix in which each column is a corresponding degree of x. So first we construct this matrix using this function, extend features. Here it's quite simple. We pass this matrix to the function fit. So a regression model is trained and use the function predict on using this trained regression model. So, and here the results. We define the case equal to 15, and we can clearly see that the model overfits the data. It passes good through the training points here in this area, and has high errors on the test points that are red. It's a consequence of too weak inductive bias. We have chosen too complex class of models. It's much more complex than the complexity of the function under modeling. It was the polynomial of degree 3. Both models, linear and with polynomial with k equal to 15, these models are bad models. They have high test error, but the source, the nature of this error is different for these models. So let's go further. We will generate training data many times. We use for loop, and in each loop we generate random data, split them into training and test sets, and fit the regression model. Then we plot the regression function. So let's run. For simple regression model for k equal to 1. Well, here we can run here. Here. So let's look at the results. We can see that all these regression models, linear regression models, are approximately the same. In other words, the regression model slightly depends on the specific training data. Every time we have used different training data, and we obtain approximately the same results. Well, every model each of these models is bad model. It's obvious. And now we will repeat this experiment for higher degree, for example, 30 degree. We will repeat it many times. And every time we obtain different results. What we can note here. We can see that the models work in different ways on the bounds of the interval. It's a feature of polynomial models, but if we choose some other class of models, for example, neural networks, these peculiarities can occur in every part of the interval. So we can observe the different source of error for the case of underfitting and let's run once again, and for overfitting. In the first case, in the case of underfitting, the model has high error due to so-called bias. That is the difference between the averaged response of the models and the true function. That is our polynomial. And in the case of overfitting, the error is high due to the variance, that is the high sensitivity of a particular trained model to the trained data. But in this case, the average, if we train infinite number of models and average responses, we obtain a good approximation of the true function. The concept of bias and variance can be illustrated using dartboard. The dartboard is a hypothesis space. The bullseye is the true function, and the darts are learned models. If we chase strong inductive bias, we will obtain bad, but almost the same models. As in the case of linear regression function. All models are bad, but they are approximately the same. So we are precise, but our gunsight has a bias. In the case of too weak inductive bias, we are not precise in every single shot. But in the average, we are near to the bullseye. And the perfect case, when we chase a good inductive bias, the model has low bias and low variance, and hence low error. The inductive bias and the generalization capabilities depend on the model complexity. Too simple model leads to high bias but low variance, and too complex model leads to high variance and low bias. And there is some optimal complexity of the model between these extreme cases. The optimal complexity depends on the training data, and its estimation is one of the problems that machine learning deals. At this point, if we finish, so in this lesson, we have introduced some concepts and problems in supervised machine learning, and I invite you to the cybernetics department of NRNU-MFE to study these topics deeper and continue investigating this area. So thank you for your attention.